Before we begin, find yourself somewhere comfortable. This is a story told at the pace of starlight, meant for those quiet hours when the mind is ready to wander and wonder. If your thoughts drift, if sleep finds you along the way, that's perfectly natural. The sun has been telling its story for 4.5 billion years. It will wait for you. December 2025, the winter solstice. Half the world tilts away from the sun, wrapped in the longest night of the year. While we sleep beneath the darkness, something quiet and extraordinary is happening 93 million miles away on the face of our closest star. A wound has opened. Not a wound of blood or flesh, but something stranger. A wound of absence. A vast dark region stretching across the solar surface, visible only through the specialized eyes of telescopes that can capture ultraviolet light, at wavelengths our eyes were never designed to see. If you could look at these images, it would seem as though someone has torn a hole straight through the sun itself. The darkness spreads from the northern hemisphere, slices through the solar equator, and plunges deep into the southern regions. Scientists have given this phenomenon a name that sounds almost medical. They call it a coronal hole. And this particular one, emerging in these final weeks of the year, is among the largest we've observed in this young century. The numbers tell part of the story, though numbers can feel cold when we're talking about something so vast. 500,000 miles across. That's roughly 62 times the diameter of Earth. You could line up our entire world, this blue marble we call home, 62 times and still not span the width of this dark emptiness. It's the kind of scale that makes the mind hesitate, searching for some way to truly comprehend what 93 million miles of distance can barely diminish. But calling it a hole carries a strange contradiction. The sun hasn't actually developed a gap in its surface, some tear in the fabric of its being. What we're witnessing is something far more subtle and far more fascinating for those of us living on the third rock from this ancient fire. To understand what a coronal hole truly represents, we need to step back and remember what the sun actually is. Our star is not a solid ball. It's a churning sphere of plasma, that fourth state of matter where temperatures become so extreme that atoms themselves come apart, losing their electrons and becoming electrically charged particles drifting in a sea of energy. Deep at the core, where temperatures climb to 27 million degrees, hydrogen atoms fuse into helium, releasing the energy that makes all life on Earth possible. But the story of these coronal holes begins much farther out, in the outermost layer of the solar atmosphere, the corona. The corona is a region of beautiful contradiction. While the visible surface of the sun, that bright photosphere we should never look at directly, registers at roughly 10,000 degrees Fahrenheit, the corona somehow reaches temperatures of 2 to 3 million degrees. For decades, this mystery puzzled the scientists who studied our star. How could the outer atmosphere be hundreds of times hotter than the surface below it? It seemed to violate everything we understood about heat flowing from hot to cold, about energy dissipating as you move away from a source. The answer, when it finally emerged, lay in something invisible. Magnetic fields. Those invisible lines of force that thread through the sun like a vast three-dimensional tapestry. Like an architecture we can never see with our eyes but can trace through their effects. When these magnetic field lines twist and snap and reconnect, they release tremendous energy that heats the surrounding plasma to those extraordinary temperatures. Imagine for a moment that you could see magnetic fields, not with your eyes, which detect only that narrow slice of the electromagnetic spectrum we call visible light, but with some enhanced sense that reveals the invisible architecture threading through space. If you looked at the sun with such vision, you would see something extraordinary. Lines of magnetic force erupting from the surface, curving through the corona in graceful arcs, and diving back down again. These closed loops trap plasma like invisible bottles, holding superheated gases in place and causing them to glow brilliantly in ultraviolet and X-ray wavelengths. But in certain regions, you would see something different. Lines of magnetic force that don't loop back at all. Instead, they stretch outward, extending deep into space like highways with no return, like rivers that flow only in one direction. These are the open field regions, and the plasma here is not trapped. It flows outward along these magnetic highways at tremendous velocities, leaving behind a region that is cooler, less dense, and darker than its surroundings. This is what we call a coronal hole. The term wasn't always in use. Early astronomers studying the Sun had no way to see these features directly. The corona itself was invisible except during total solar eclipses, those rare and precious moments when the Moon blocks the blinding solar disk and reveals the pearly white atmosphere surrounding it. Some eclipse photographs from the 19th and early 20th centuries hinted at darker regions near the poles, but without the ability to see in ultraviolet light, scientists could not understand what they were observing. The breakthrough came with the Skylab mission in 1973. For the first time, astronauts and instruments floating above Earth's atmosphere captured soft X-ray images of the Sun with unprecedented clarity. There, unmistakably visible, were vast dark regions in the corona. The invisible had become visible, and a new chapter in our understanding began to unfold. Today, we observe coronal holes routinely, almost casually, using spacecraft like NASA's Solar Dynamics Observatory and the joint missions that keep their unwavering gaze pointed at our star. These instruments capture images at specific wavelengths, particularly around 193 angstroms in the extreme ultraviolet range, where the contrast between normal corona and coronal holes becomes most striking. The physics of why coronal holes appear dark carries an elegant simplicity once you understand the mechanism. The closed magnetic loops of the normal corona trap plasma at temperatures of 1 to 2 million degrees Kelvin, and this superheated gas radiates intensely in ultraviolet wavelengths. But in coronal holes, where the magnetic field lines open into interplanetary space, the plasma is free to escape. What remains is cooler, typically 700,000 to 1 million degrees Kelvin, still unimaginably hot by any earthly standard, but cool enough and sparse enough to appear dark when compared to the surrounding brilliance. Think of it like a pot of boiling water. With a lid, the pot traps the steam, keeping everything hot and roiling. Remove the lid and the steam escapes. The pot cools. The coronal hole is the region where the magnetic lid has been removed, allowing the solar atmosphere to vent into space. Long before humans understood that the Sun was a star, long before we knew about magnetic fields or the physics of nuclear fusion, careful observers noticed something peculiar. Dark spots appeared on the face of the Sun, grew, shifted position, and eventually faded away. The Chinese recorded such observations as early as 800 years before the Common Era. Greek philosophers debated what these blemishes might mean for a celestial body they believed should be perfect and unchanging. But it wasn't until the early 17th century, when Galileo turned his telescope toward the Sun, that systematic study of sunspots truly began. What Galileo saw challenged everything Europe believed about the heavens: dark patches, irregular in shape, moving across the solar disk as the Sun rotated. Some lasted weeks before vanishing, while others appeared suddenly in regions that had been clear just days before. The Sun was not a flawless sphere of divine fire. It was dynamic, changeable, subject to forces no one yet understood. Over the following centuries, astronomers accumulated observations with the patience that science requires. Among them was a German pharmacist named Samuel Heinrich Schwabe, who spent 17 years obsessively tracking sunspots, drawing the solar disk day after day between 1826 and 1843. His persistence, that quiet dedication to watching and recording, revealed a pattern no one had suspected. Sunspot numbers rose and fell in a regular rhythm, peaking roughly every 10 years before declining to minimum levels. Schwabe had discovered the solar cycle. Further refinements by other patient observers pinpointed the average length at approximately 11 years, though individual cycles vary from as short as 9 years to as long as 13. The Swiss astronomer Rudolf Wolf standardized methods for counting sunspots and reconstructed historical records all the way back to 1755, which marks the beginning of what we now call Solar Cycle 1. We are currently in Solar Cycle 25, which began in December of 2019 and will likely continue until around 2030. But what causes this 11-year heartbeat? Why does our star pulse between quiet phases with few or no sunspots and active phases where the solar surface erupts with dozens of dark patches, explosive flares, and billion-ton ejections of plasma? The answer lies in the Sun's magnetic field and its extraordinary behaviour. Unlike Earth, which has a relatively stable magnetic field generated by its solid iron core and liquid outer core, the Sun generates its magnetic field through a process called the solar dynamo. The Sun is not solid, remember. It's a sphere of plasma that rotates, and it doesn't rotate uniformly. The equator completes one rotation in about 25 Earth days, while regions near the poles take closer to 35 days. This differential rotation stretches and twists magnetic field lines that initially run from pole to pole. Imagine taking a rubber band stretched between the top and bottom of a spinning sphere, then spinning the middle faster than the ends. The band would wrap around the equatorial regions, becoming increasingly wound and distorted. This is essentially what happens to the Sun's magnetic field over years of rotation. The field that once ran cleanly from north to south becomes wrapped around the Sun's interior like coils around a cylinder. These concentrated magnetic field lines eventually become unstable, rising buoyantly through the solar interior and puncturing the surface in paired loops that we observe as sunspot groups. Sunspots appear dark because the intense magnetic fields within them suppress convection, preventing hot plasma from welling up from below. The result is a region roughly 3,000 degrees cooler than the surrounding photosphere, cool enough to appear black by contrast, though still blazing at nearly 7,500 degrees Fahrenheit. And here's where the story becomes even more remarkable. When the next 11-year cycle begins, everything flips. The Sun's entire magnetic polarity reverses. What was the magnetic North Pole becomes the magnetic South Pole, and vice versa. This means that the true cycle of the Sun's magnetic field is not 11 years, but roughly 22 years. After 2 activity cycles, the Sun returns to its original magnetic configuration, and the Great Rhythm begins again. In 1958, a young physicist named Eugene Parker proposed something that seemed radical to his colleagues. He suggested that the Sun was not simply radiating light and heat into an empty void, but was actually exhaling, continuously streaming charged particles outward at tremendous velocities, filling the entire solar system with a thin but constant flow of solar material. He called this flow the solar wind. His colleagues were skeptical, and some were openly hostile to the idea. The notion that plasma could continuously escape the Sun's immense gravity and pervade interplanetary space seemed to contradict fundamental thermodynamic principles. One prominent scientist even recommended that Parker's paper be rejected from publication, but the editor chose to publish it anyway, trusting in the mathematics and reasoning even when intuition resisted. Within 4 years, spacecraft measurements from the Soviet Luna 1 and American Mariner 2 confirmed that Parker had been right all along. The solar wind is real, it is everywhere, and it fundamentally shapes the space through which all planets move. To understand the solar wind, you must first appreciate the extraordinary temperatures of the solar corona. While the visible surface of the Sun registers at roughly 5,500 degrees Fahrenheit, the corona reaches temperatures of 1 to 3 million degrees. At such extreme temperatures, the thermal energy of individual particles exceeds the gravitational binding energy of the Sun itself. They can escape, and escape they do in numbers beyond ordinary comprehension. Every second, the Sun loses approximately 1 million tons of material to the solar wind. That sounds like an enormous amount, and it is by any human measure. But the Sun contains roughly 2,000 trillion tons of matter. At the current loss rate, it would take 150 billion years for the solar wind to carry away even 1% of the Sun's mass. Our star can afford to be generous with its outflow, breathing out this constant stream without diminishing itself in any way we could measure across human timescales. The composition of the solar wind reflects the composition of the Sun itself. Approximately 95% consists of protons, which are simply the nuclei of hydrogen atoms. Another 4% comprises alpha particles, helium nuclei containing 2 protons and 2 neutrons. The remaining 1% includes heavier ions, electrons, and trace amounts of other elements. All of this forms an electrically conductive gas, a plasma threaded through with magnetic field lines. Those magnetic field lines prove crucial to understanding how the solar wind behaves. As solar wind plasma streams outward from the Sun, it carries embedded within it the magnetic field of the solar corona. This interplanetary magnetic field doesn't simply point straight outward, because the Sun rotates while the plasma flows away. The field lines curve into a spiral pattern, like water spraying from a spinning garden sprinkler. This elegant geometry is called the Parker spiral, named after the same Eugene Parker who predicted the solar wind's existence. Not all solar wind travels at the same speed. Slow solar wind, typically originating from regions of closed magnetic loops near the Sun's equator, moves at 300 to 400 kilometers per second. Fast solar wind, streaming from those coronal holes where magnetic field lines open directly into space, can reach 600 to 800 kilometers per second or even faster. At these velocities, slow solar wind takes 4 to 5 days to reach Earth, while fast solar wind can arrive in just 2 to 3 days. When the solar wind arrives at Earth, travelling across that vast distance of 93 million miles, it encounters something remarkable: our planet's magnetic shield. Earth is surrounded by a magnetosphere, a region of space dominated by our world's own magnetic field. This field is generated deep within Earth's core, where the rotation of liquid iron creates a dynamo effect, similar in principle to the Sun's dynamo but operating on vastly different scales. The magnetosphere extends tens of thousands of miles into space on the dayside facing the Sun, and stretches into a long tail millions of miles long on the night side. When the solar wind reaches Earth, it cannot simply penetrate this magnetic barrier. Plasma cannot easily cross magnetic field lines, so instead the solar wind flows around the magnetosphere like water, flowing around a rock in a stream. On the sunward side, it compresses the magnetosphere, pushing the boundary called the magnetopause closer to Earth. On the nightward side, it stretches the magnetosphere into that elongated tail. The pressure of the solar wind determines where this boundary sits. Under normal conditions, the magnetopause rests roughly 10 Earth radii from the surface, about 40,000 miles out. But during periods of high solar wind pressure, such as when a high-speed stream from a coronal hole impacts our world, the magnetopause can be pushed inward to 6 Earth radii or less. Satellites in geostationary orbit sitting approximately 22,000 miles up can find themselves momentarily outside the protection of the magnetosphere. The most significant factor in how the solar wind interacts with our magnetic field is not the speed or density of the incoming plasma, but something more subtle: the orientation of the interplanetary magnetic field. When this magnetic field has a southward component, pointing opposite to Earth's northward pointing field, a process called magnetic reconnection becomes more efficient. The two opposing fields can merge and reconfigure, transferring energy into our magnetosphere and producing what we call geomagnetic storms. These storms manifest in ways both beautiful and challenging. Magnetometers in northern latitudes record fluctuations in Earth's magnetic field strength. The aurora oval, that ring of dancing lights encircling the polar regions, expands southward. People who have never seen the northern lights suddenly spot them from backyards in Montana, Washington, and the upper Midwest. But the beauty exists alongside more practical effects. Satellites orbiting Earth experience increased drag as the upper atmosphere swells with energy from geomagnetic storms. GPS signals can degrade as the ionosphere becomes disturbed. High-frequency radio communications used by aircraft over polar routes may black out for hours. Power grids experience voltage fluctuations as geomagnetically induced currents flow through their long transmission lines. In 1989, a geomagnetic storm demonstrated these effects clearly when it knocked out power across Quebec, leaving 6 million people without electricity for 9 hours. That storm was rated moderate on the scale of historical events. We are learning slowly and steadily how to anticipate these moments and protect the systems we've built. It's a process of adaptation, of understanding the rhythms of our star and learning to move with them rather than against them. The story takes us back to September of 1859, to a morning that began like so many others for Richard Carrington, a British astronomer who had made it his practice to observe the sun. Carrington was one of those patient observers, the kind who returns day after day to watch and record, building understanding through dedication rather than dramatic breakthroughs. On the morning of September 1st, he was in his private observatory, projecting an image of the sun onto a screen, drawing the sunspots as he had done countless times before. What happened next was something Carrington had never witnessed in all his years of observation. 2 brilliant patches of white light appeared among the sunspot groups, intensifying over the course of about 5 minutes before fading away. He had just witnessed what we now call a solar flare, one of the most powerful ever recorded, though he had no framework at the time to understand what he'd seen. The light was so intense that it was visible even against the brightness of the sun itself. 17 hours later, the effects reached Earth. What followed became known as the Carrington Event, the most powerful geomagnetic storm in recorded history. The auroras that appeared that night were unlike anything in living memory. They were visible as far south as the Caribbean, as far north as tropical regions that had never seen such lights. People in the Rocky Mountains woke in the middle of the night thinking dawn had arrived, so bright were the auroral displays overhead. In some places, you could read a newspaper by the light of the aurora alone. The telegraph systems of the era, which represented the cutting edge of communication technology, experienced extraordinary disruptions. Telegraph operators reported receiving electrical shocks from their equipment. Some telegraph lines continued to operate even after their batteries were disconnected, powered entirely by the electrical currents induced by the geomagnetic storm. Papers burst into flame from the intensity of the currents flowing through the wires. The technology that had seemed so solid and reliable proved vulnerable to forces streaming from the sun. But here's what's remarkable when we look back at that morning and the night that followed. The world adapted. Telegraph operators found workarounds, systems were rebuilt, and within days communication resumed. The disruption was significant, but not catastrophic for a world whose technology was still in its relative infancy. A Carrington-level event today would interact with a far more complex and interconnected technological landscape. Power grids could experience widespread failures, satellites might be damaged or destroyed, GPS systems could become unreliable, and the cascading effects through our digital infrastructure could persist for months. Yet even knowing this, there's something almost comforting in the historical perspective. The Carrington event happened, the world witnessed something extraordinary, adapted and continued. We're not helpless observers anymore either. We have spacecraft monitoring the sun continuously, forecasting systems that can provide warnings, and protocols being developed to protect critical infrastructure. We're learning from history rather than simply repeating it. There's a question that has intrigued some researchers, one that sits at the boundary between established science and emerging possibility. It's the kind of question that invites curiosity rather than certainty, wonder rather than conclusions. Could the sun, 93 million miles away, somehow influence the ground beneath our feet? Could solar activity and earthquakes be connected in ways we're only beginning to understand? The idea sounds almost impossible at first consideration. The sun influences our atmosphere, our magnetosphere, the space around our planet, but the solid rock of Earth's crust and mantle, that seems too far removed, too insulated from the reaches of solar wind and magnetic fields. Yet emerging research has found statistically significant correlations between proton density in the solar wind and the occurrence of large earthquakes worldwide. Studies published in prestigious journals like Nature have documented these patterns, and the data is becoming increasingly difficult to ignore. The mechanism remains debated and uncertain. How exactly would charged particles from the sun interact with tectonic processes deep within Earth? Several hypotheses have been proposed. Some researchers suggest that variations in solar wind pressure could subtly affect Earth's rotation rate, and these tiny changes might influence stress patterns in fault zones already near their breaking point. Others point to possible electromagnetic effects, where strong geomagnetic disturbances could interact with the electrical conductivity of Earth's mantle and crust. Still others explore connections through atmospheric pressure changes induced by solar activity. What makes this particularly intriguing is the timing. 2025 has already proven to be one of the most seismically active years on record. The timing of earthquake swarms coinciding with solar wind impacts has raised eyebrows among researchers willing to investigate connections that mainstream science once dismissed as fringe speculation. The correlation doesn't prove causation, of course. That's one of the first lessons in understanding scientific research. But correlations that persist across large datasets and multiple studies deserve investigation rather than dismissal. It's worth sitting with the uncertainty here, letting it be what it is. Science doesn't always provide immediate answers, and some of the most fascinating areas of research exist in these borderlands where connections seem possible, but mechanisms remain mysterious. The relationship between solar activity and earthquakes, if it exists as more than statistical coincidence, would reveal something profound about how interconnected the systems of our solar system truly are. We tend to think of Earth as isolated, protected by distance and atmosphere from the influences of space. But perhaps we're more embedded in the sun's extended environment than we've understood. The research continues quietly, patiently, as good research does. Data accumulates, patterns are analysed, hypotheses are tested and refined. Some studies find support for the connection, others find the correlations weaker than initially suggested. This is how science progresses, not through dramatic revelations but through careful accumulation of evidence and honest acknowledgement of what we don't yet know. Whether or not the Sun-earthquake connection proves to be real and significant, the very question reminds us of something important. We live not on an isolated world, but within the extended atmosphere of a dynamic, sometimes unpredictable star. The coronal hole staring at us right now is a reminder that 93 million miles offers less protection than we might hope. The Sun sneezes and Earth catches a cold. The Sun opens a wound in its corona and our satellites wobble. Our power grids strain. Our auroras dance. And perhaps, just perhaps, even our tectonic plates respond in ways we're only beginning to measure. For decades, humanity observed the Sun from a distance, from the safety of Earth's orbit and the protection of our magnetic shield. We built telescopes, launched satellites, and gathered data about our star while maintaining a respectful distance from its immense heat and radiation. But there remained questions that could only be answered by going closer, much closer than anyone had dared before. In August of 2018, NASA launched a spacecraft unlike any that had come before it. The Parker Solar Probe was designed to do something that sounds almost mythological: to touch the Sun. Not literally, of course, but to dive through the corona, flying closer to our star than any object in human history. The mission carried particular significance because it was named after Eugene Parker, the physicist who predicted the solar wind in 1958. He was still alive to witness the launch, one of the rare times NASA named a mission after a living scientist, a recognition of how fundamentally his insights had changed our understanding of the Sun. The engineering required to achieve this mission is extraordinary in its elegance. Parker Solar Probe travels at speeds reaching 430,000 miles per hour, making it the fastest human-made object ever built. At its closest approach, it passes within just over 3 million miles of the solar surface, enduring temperatures that reach 1800 degrees Fahrenheit. To survive these conditions, the spacecraft hides behind a heat shield made of carbon composite foam, just 4.5 inches thick, yet capable of keeping the instruments in the shadow side at a comfortable room temperature, while the sun-facing side glows at those extreme temperatures. What Parker has discovered is rewriting what we thought we understood about our star. During its close approaches to the Sun, the spacecraft has flown through coronal hole interiors, providing the first direct measurements of plasma conditions in regions where fast solar wind originates. Among its most intriguing findings are structures called switchbacks, dramatic reversals of the magnetic field that suggest complex dynamics in how the solar wind accelerates. These switchbacks appear as sharp zigzags in the magnetic field, like the Sun's magnetic field is folding back on itself in ways theoretical models hadn't predicted. The spacecraft has also measured the composition, temperature and velocity of the solar wind at its source, revealing signatures that help us understand not just what flows past Earth, but why it flows at all. Each close pass, each orbit that brings Parker screaming through the corona, adds pieces to the puzzle of how our star works. There's something deeply moving about this achievement when you pause to consider it. A species that evolved on a small world, protected by atmosphere and magnetic field from the harshness of space, has built an emissary to touch the fire that gives us life. Eugene Parker lived to see his theoretical predictions about invisible rivers of plasma confirmed not just by distant measurements, but by a spacecraft bearing his name diving through those very rivers. He passed away in 2022, but the probe continues its mission, sending back data that will occupy scientists for decades to come. Parker Solar Probe will continue its observations through at least 2025, completing 24 close passes through the corona. Each orbit brings it slightly closer as Venus gravity assists gradually tighten the spacecraft's trajectory. With each pass, we learn more about the magnetic fields that shape coronal holes, the processes that heat the corona to those impossible temperatures, and the mechanisms that accelerate the solar wind to the speeds that eventually wash over Earth. Of all the ways the Sun touches Earth, few are as beautiful and immediate as the aurora. When that high-speed solar wind from a coronal hole collides with our magnetosphere, When magnetic reconnection transfers energy into Earth's protective shield, something extraordinary happens in the upper atmosphere. The invisible becomes visible, physics becomes poetry, and the night sky transforms into a canvas of moving light. The process begins about 60 to 200 miles above Earth's surface, in the thermosphere and ionosphere, where our atmosphere is so thin it's nearly a vacuum. Charged particles from the solar wind, guided by Earth's magnetic field lines, spiral downward toward the polar regions. As these particles collide with oxygen and nitrogen atoms in the upper atmosphere, they transfer energy. The atmospheric atoms become excited, jumping to higher energy states, and when they return to their normal states, they release that energy as light. The colours tell us what's happening and where. Green, the most common aurora colour, comes from oxygen atoms at altitudes around 60 to 150 miles. Red auroras, rarer and often appearing higher in the sky, also come from oxygen, but at altitudes above 150 miles, where the atmosphere is thinner and collisions happen more slowly. Blue and purple hues emerge from nitrogen, adding depth and complexity to the displays. During strong geomagnetic storms, when a particularly powerful solar wind stream impacts Earth, the aurora oval expands. That ring of light that normally encircles the magnetic poles pushes southward in the northern hemisphere, northward in the southern hemisphere. People who have never seen auroras, who live far from polar regions, suddenly find themselves standing beneath curtains of light that seem to dance and flow across the darkness. In Montana, in Washington, in the upper Midwest, backyards become theatres for cosmic display. The movement of auroras reflects the dynamic nature of the processes creating them. The dancing, the rippling curtains, the sudden flares of brightness, these result from fluctuations in the solar wind, variations in the magnetic field, and the complex physics of how energy transfers from magnetosphere to atmosphere. No two auroral displays are exactly alike, each one a unique expression of the interaction between Sun and Earth at that particular moment. Humans have watched these lights for as long as we've existed in northern and southern latitudes. The aurora borealis, the northern lights, and aurora australis, the southern lights, appear in the mythologies and legends of cultures around the world. The Norse saw the reflection of the Valkyrie's armour, spirits of fallen warriors riding across the sky. Indigenous peoples of North America developed diverse interpretations, from dancing spirits to signals from the ancestors. The Maori of New Zealand saw the aurora australis as fires lit by their ancestors. Before we understood plasma physics and magnetic reconnection, we reached for stories to explain beauty we couldn't categorize. There's something deeply moving about standing beneath an aurora. If you've ever had that privilege. The lights don't make sound, despite persistent reports across centuries of whistling or crackling noises during intense displays. Scientists still debate whether these sounds are real or psychological, but the silence is part of the magic. The aurora unfolds in perfect quiet, this enormous release of energy painting the sky while you stand small and still beneath it, your breath making clouds in the cold air. Photography has made auroras more accessible, allowing people far from polar regions to witness displays through images shared instantly around the world. But something is lost in the translation from experience to image. A photograph captures a moment, but the aurora exists in time, constantly moving and changing. The way a curtain of green light suddenly flares, the way colours shift and blend, the sheer scale of light stretching from horizon to horizon, these demand presence, attention, the willingness to stand in the cold and watch. The December 2025 coronal hole that opened this story has brought auroras to latitudes that don't often see them. Each time the high-speed stream from that wound in the sun's corona sweeps past Earth, the skies respond. It's a visible reminder of the connection between our world and our star, a connection that exists whether we see it or not, but occasionally makes itself known in green and red and purple light. The dark wound on our star is not closing. If anything, the patterns suggest more and larger coronal holes in the years ahead as we descend from solar maximum towards the next minimum around 2030. Each one will send its river of charged particles washing over our world. Most of the time our magnetic shield will hold, the disruptions will be minor, and the auroras will be beautiful. We are learning slowly and steadily what it means to be a technological civilization living within the extended atmosphere of an active star. The sun is not quiet. It's not predictable in the ways we once hoped it might be. Solar Cycle 25 surprised forecasters with its strength. Scientists initially predicted it would be weak, similar to the underwhelming cycle before it, but they were wrong. The Sun exceeded predictions by significant margins, producing stronger flares, larger coronal holes, and more intense space weather than models suggested. This unpredictability is not a failure of science, but a recognition of complexity. The Sun is a sphere of plasma with magnetic fields that twist and reconnect in ways we're still working to understand fully. Each solar cycle teaches us more, refines our models, improves our ability to forecast when a coronal hole might form and how its high-speed wind stream might affect Earth. We have spacecraft positioned between Earth and the Sun, providing early warning when disturbances are heading our way. We have protocols developing for protecting power grids during extreme events. We're adapting, as humans have always adapted to the environments we find ourselves within. The broader perspective helps here, the view from deep time. The Sun has burned for 4.5 billion years and will continue burning for 4.5 billion more. It will exhaust its hydrogen eventually, expand into a red giant, and ultimately shed its outer layers to become a white dwarf. But that transformation lies so far in the future that it exists beyond the scale of anything human. For now, for all the time that matters to us and countless generations to come, the Sun will continue its 11-year heartbeat, its breathing out of solar wind, its occasional powerful outbursts. Understanding what is happening 93 million miles away has become essential knowledge for a technological species. The Sun gives us life through the steady warmth and light that makes Earth habitable. It can also remind us, with humbling force, that we remain small creatures on a small world, subject to the whims of a star that operates on scales vastly beyond human control. But subject to doesn't mean helpless. We observe, we measure, we learn, we prepare. The wound is open, yes, this coronal hole dominating the December sky. Its high-speed solar wind will continue streaming towards Earth with each 27-day rotation of the Sun. More coronal holes will form as the solar cycle continues its descent. Geomagnetic storms will arrive, some mild, some significant. Auroras will dance across skies that don't often see them. Satellites will adjust their orbits. Power grid operators will monitor their systems, and life will continue. We live not on an isolated world, but within something larger, within the heliosphere created by our star's constant exhalation. 93 million miles offers less protection than we might hope, but it offers enough. The Sun sneezes and Earth catches a cold. But we've survived every solar cycle that's come before, every coronal hole, every geomagnetic storm. We'll navigate what comes next too, with greater understanding and better preparation than any generation before us. The Sun will continue its ancient rhythm, and we'll continue learning to live within that rhythm, respecting its power while marvelling at its beauty. The stars will continue their ancient dance, whether we watch or sleep. The Sun will rise again tomorrow, carrying with it all these invisible rivers and magnetic architectures we've explored together, and somewhere, perhaps, auroras are painting silent colours across a darkening sky, a reminder that we're held within something vast and beautiful. Rest well,